Hey, what's up, guys? This is Chung here again. So today, let's take a look at the last problem of this week's weekly contest, which is number 1632, rank transform of a matrix. Yeah, I think this problem is definitely a hard problem. Okay, so mm, let's take a look at the problem description first. So you're given like a m times n matrix, and it asks you to return a new matrix answer, which the each element on this answer is the rank of the previously matrix. So the way the rank works is that the ranking is only representing on each row and column, not the entire matrix. So which means that on the same row, the bigger number is always has the higher rank than the lower number, and same thing on the column. And the second and the And the last constraint is the rank should be as small as possible. So if it's one, then it should be starting from one. So a few examples here, right? So for example, it's one, two, three, four. We got one and two, of course, is one and two, and three and four is two and three. So why is that? Because the one and two is one and two, but one and three we also need to put because three is bigger than one, right? So on the column wise, we have to put two here. But then again on this column on this row wise, right? Since four is bigger than three, so that's why we have three here. And this is another example. So everything is seven. That's why everyone has a one because the same number have the same number will have the same ranking, right? So this is like a more complicated solution examples here. We'll take a look at this one later on. Okay, so mm, okay, so where should we start, right? So to solve this problem, there are like a few prerequisites you guys need to know first. So the first one is a problem 1331. It's called rank transform of array. So as you guys can see, the name is almost the same, but instead that one is an array, it's 1D, right? But this one is a matrix. So if you guys haven't solved that problem, I highly recommend you to do that problem first. Anyway, that's an easier problem. And this one is just an extension of that one. So to solve this kind of ranking problem, the common way is to sort. Even for that easy problem, we sort that 1D array and then we process from the smallest to the biggest. Okay, so that's a good start for this problem, which means for this problem, we also need to sort all the arrays, sorry, all the numbers on this 2D matrix here. But we cannot simply we cannot simply increase the ranking by each number. So like I said, since the constraints for this problem is we only need to guarantee the sortings on the column and the row wise, not the entire matrix, right? I mean, for example, this one, if we sort it from everything else, from start to the end, we'll get one, two, three, and four, right? So that's the sorting we're getting. But instead, all we need is two and three on the second row here. Okay, so how can we solve that problem? So next is we need to make some observations. Um, which one we should use? Maybe this one. I think this is a good example here. So first, we know we want to sort from the smallest number to the biggest number. Okay. And second, what's going to be the second approach here? So the second observations we need to make here is that assuming we have uh, since we have 2D matrix here, what does it mean? It means that let's say we have two fours, right? We have two fours on this either the same row or the same column. Same thing for this 19, right? As you guys can see here, so the same number that on the same basically sharing the same column or row or the columns will definitely have the same number. It's simple, right? It's simple. It's pretty straightforward, right? Because they are the same numbers, and we want to maintain the sortings on the column and row and column wise. So that's why if the number is on the same row and or column, they must have the same number. But which number they should have, right? That's okay. That's why we use this sorting plus. So when we use the sorting, it's kind of like greedy approach. So it's as you guys can see, so this four is on this row and column, and this four is on this row and column. So it means that we need to maintain like the current maximum row rank and the current maximum column rank. Okay. So why is that? I mean, let's take one example, right? Let's say there's only one four here. And when we are processing this 4 here, let's say there's no this 4, we only have this one 4. And assuming we are processing numbers from the smallest to the biggest, right? And when we're at this 4 here, which rank we should give it, right? What we should give? It should, so basically this 4, we need to compare what's the current maximum ranking on this column and what's the current maximum ranking on this row, right? Let's say we have the current max ranking is 2 on this column, and is 3 on this 3 on this. Okay, not maybe not 3 here. Let's say it's 5. It's 5 on this row. So what we should have here, of course, we need to get, since we need to satisfy both the row sortings, the row ranking and the column rankings. That's why we need to get the maximum out of the current row ranking and the current column ranking, and we do a plus one. So which means we have 5 plus 1. That's how we get 4. So sorry, that's how we get 6. Right? So this is not that hard to understand, right? So that's just one number. Okay. Now another the difficulty is really what if we have more than one numbers on the same row and column? For example, this one, right? So this is also a 4. And since we already find out that for the same numbers on the same row or column, they should have the same ranking. So what does it mean? It means that okay, so if we use 6 here, right? So if we use the 6 here, it might not satisfy the okay, it will definitely satisfy this column here, but it might not satisfy this row here because this row might have like what? It might have like 7, right? So if we put 6 here, that will basically, and also keep in mind we're processing the numbers from smallest to the biggest, so which means that this 4 is definitely bigger than the numbers we have already placed on this row here. So what does it mean? It means that if we have more than one numbers on the same row or columns, we have to get all their rows. Basically, we need to query all the same numbers, rows and columns, and we need to get the maximum out of it, and then we use that one as the ranking for all the numbers. So for example, this one we have 5, 6, but we have 7 here. So which means here we need an 8, right? So which means that here instead of 6, we also need to put an 8 here. Okay, that's how we calculate this one. And after setting these things here, we also need to update the maximum row and column, right? So now the maximum row and column for this one, for this row, for this column, and for this 2 row, they all become 8, and we keep going forward, right? So that's the basic idea to solve this problem. And now now the problem comes down to how can we find the same numbers, right? Same numbers on the numbers with the same values on the same row and column. There are like a few ways, different ways you can do it. I mean, the first way is you can use like a BFI search or DFI search, right? Basically, you at one numbers here, you go up, left, down, and right. You go four directions. You're trying to find the same numbers, right? And then you store it somewhere, right? And then later on you process them. Or another way is you use union find. Okay, I think actually I prefer using union find because the union find is very useful in many other problems. So I figured it's a good practice to do here. But the union find is a little bit tricky here, because it's not like a Uber union find here, there's no single parents here on the very top. So why is that? Because basically we're using the union find for each of the number, for each of the value, for each of the numbers, right? Basically, there could have like how many numbers we could union at one location. There could be like m m plus n numbers, right? So that's the numbers on this crossing here. And basically, we need to have like a union find array for each of the number here. That's why we cannot simply define like a Uber union find like a parent, right, at the top. So we have to define it in the for loop. Okay, so let's start coding here. So the coding will be a little long here, but stay with me, guys. I know this is a hard one, but it's a good one to learn. Okay, so we have a m and n, right? So that's okay. So let's define the union find template first, right? So for the find, we have like an x, right? And if x is not equal to the parent x, right? So we're doing like a path compression here. Parent x equal to the find parent x here. Okay, and then later on we return the parent x. So for those who don't know the path compression and the templates of Unified, you can easily find any like some materials online or videos, right, to explain to you why we're doing the find here. Basically, we are trying to find the common root for this x, and while we're finding that root, we also reassign. We're cutting the path. We're cutting the path from here. So like this, I'll try to explain this one more time here. Right? So let's say this is the root here, because at the beginning, all the numbers have has its own as a root. Okay. And while we're let's say we want to find this number 4 here, and this is the root. So while we're finding this thing here, right? So the parent is equal to this parent equal to this. We're using like a recursive function, and while we're doing that, we're basically moving this 4 below below this root here. Let's say this is 3, so we're moving 3 below this root here. That's how we do the path compression. Okay, and then the union, right? Define a union. Okay, we have a union here and x and y, right? So that's another template for the union. We find the root for the x, and we find the root for the y, right? So sorry, y, and then if the R1 is not equal to R2, we do a union find. It doesn't really matter which way we assign here. We could have used the ranking system, but here it doesn't really matter. So the path compression is good enough to allow us pass this test case here. Okay, so that's the template, and now we need to sort, right? So let's do the sorting first. So how do we do sorting? We sort by the what? We sort by the value, right? So that's which means we need a value to what? To index maybe value to position. Okay, so I'll do a value to position here. So default dictionary list here. because for each value, for example, this one we have 1 here, right? I'm sorry, we have a 19 here. A 19 could have like multiple places. Maybe we have another 19 here, right? Right. So that's why we will be aggregating the same numbers to this one list. So which means we have 4i in range m, right? And we have 4j in range n here. And we have a key here, right? So we have a value here. So the value is the matrix, right? I and j. Basically, for the same values, we add that location, that position dot value append I and j. So that later on we can use this I and j to do the union find and to update the row max and the column max ranking, right? So now we have this value to position dictionary here. Now we can just do our final loop here. So first, let me define the answer, right? So that's going to be the answer, the same size of the original matrix, right? And okay, so and then like I said, we need to have like a row max rank. So I'm defining this 0, okay, column max rank. Same thing for the n here. So again, so this one basically it records what's the current maximum rank for this row, and this is for this column. Like again, so because for each of the numbers here, we need to satisfy both the row and the column, and we get the biggest maximum out of those two, and then we do a plus one, right? So now we have a value, right? We have a key and value. So we have value in the sorted. Like I said, we need sort by this value to position, right? We sort this by the key, okay? And then what do we do? And then we will be like trying to find the same numbers, right? The same numbers for this number for this value. Sorry, the same number for the on the same row and column. That's why we need a union find list here, right? So a range like m plus n. So here, while I'm defining this parent, basically here I'm defining this union find array for this value. And why it's m and n? Because in total there could be that many numbers here, right? So we have m rows here. We have m rows, and we have n columns. Okay, that's why so the worst case, not the worst, the most values we could have union is m plus n. Actually, it's m plus n minus one, but it doesn't really matter, right? Okay, and I'm using that one. Okay, so and the way I'm representing the I and J is since the I and J they could be in the same location. They could have like I is equal to 2 and J is also equal to 2, right? But then we cannot. That's why I use m plus n here. And the way I'm mapping this J to this parent, I do a 2 plus n so that the I and J will not be conflict. Okay. All right. So now let's do the union first, right? So for I and J, so now we have I and J in its value to position value, right? So basically so here what we are doing is for every position, every I and J for the same values here, we're trying to group them together. We're trying to group them by their row and column. So as long as either they have the same row or they have the same column, they belong to the same group. Okay, right? That's how we use this union find because we're basically we're union this values row and a column. We're uniting them together. So later on, we can just use either the row and the column to find their root. And as long as they have the same root, then we know, okay, they are in the same group, right? So the union is pretty straightforward. We just do a union I and j. But remember, j, we do a j plus n. We cannot do a I plus j because this is like this is like a 1D array, right? So that's why we have to distinguish the I and j. So that's why we increase the j by n to make sure it will not collide with the I. Okay. So now what do we have in the parents here? So since they are all zero based, so it means that now anything on this parent, if they have the same parent, it means that they are on the same row and column. Okay. So now I just need to have like a root2 rank to default dictionary int. So why I'm doing this? So because currently, let's say we have like 19, 19. Let's say we have another 19 here. These two are on the same group, and let's say there's another 19 here, and these two are on the same group. So after this union find, this two 19 will have the same root, and these two 19s will have the same root. And for each of those groups here, those group we need to calculate their ranks separately because they're not on the same. Even they have the same numbers, but they are not on the same row and column. Okay. So that's why I'm creating this root to rank. Basically, the key of this is it is a root. It's a root in the union find parent list here, and the rank is their new rank. Okay. So for I, j in same thing. I'm looping through this one more time. Maybe I can do it. I can combine this to one for loop, but I'm just find this is like easier to do. And now I have a root, right? So find I. So now basically, since we have already union them together, now as long as they are on the same row and column, they will definitely have the same root here. That's why I'm using this root as a key, right? So now we have a root to rank. So the key is the root, and the value, like I said, is the new ranking for that. So if they have multiple like position, right, or coordinates that have the same root, we need to get the biggest number, the biggest out of those row and columns, right? So that's why we need to get a maximum of what? First, of course, is this, right? That's the first things we need to do since we're getting the maximum. And the second one is what? Second one is the current. For this current I and j, the current maximum is the what? It's the row max. It's the row max, right? I or the column max of I. And then of course we plus one, right? So because we need to get more. We need to be greater than the current max, right? So that's that. Do I have like another parenthesis? Okay, I think yeah. And so why I'm doing this? So this is pretty easy to understand, right? So for the current I and j, the current ranking based on this row and based on this column, it is this. But since we might have multiple might have multiple numbers, right, sharing the same root. That's why I need to loop through all the values and who is sharing the same root, and we update that value. We do a max so that we can get the maximum out of all the numbers on the same row and column. Okay. So now after this for loop, we have basically for this case we'll have two values in this root to rank. So the first one is the rank is the rank is a root rank for these two numbers, and the other one is a root rank for these two numbers. So now all it's left is what? We just need to update our answer, and also the row and the max, the row and the column max rank array here. So I'm going to do a third for loop here. I think this is kind of like a trivial, but I think it's easier to understand. So here, maybe I'll just group numbers, right? Group numbers on the same row or column. Okay, here's what the calculate new rank for the numbers which have the same root, means on the same row or column. Okay, and the last thing is what? The update the answer and the row and the column max rank, so that it can be ready for the next number. So same thing, right? We need to find the root for this current I or j. So here it doesn't really matter. We can either use I or j because we have already union this I and j together. So either I or j will give you the same root. And now we already have the rank for this root, right? So the rank is to what? It's the root dot rank is the root, right? Sorry, the root. We have the rank here. Now all it's left is what? We update the answer, right? The I and j is equal to the rank because we know that's the new rank for this I and j. Okay, same thing for this row and max. So we know here it's also needs to equal to the rank, and same thing for the column, right? Column is j equal to the rank because this one we have already calculated among all the numbers and we're getting the maximum out of it, right? So here we simply return the answer. Okay, yeah, let's try to run the code. I'm hoping I didn't make any stupid mistake here. Nope. Obviously, I have made some mistake here. Let's see. Hmm. I think here is pretty straightforward. I shouldn't have any issues here. X and Y, so this is also pretty straightforward. So we have this, and with value, okay, we create this dictionary, and we have this M and N, N and M, okay. So here value positions, parents, that's that. Let's see. Okay, I think this might be the issue here. Should be J, right? I I should use J instead of I here. That will give us definitely the wrong answer here. So other than that, it should be fine. Okay, cool. So this one is accepted. Let's try to run. All right, cool. Success. All right, pretty cool. So how about time and space complexity, right? So, I mean, we have a sort here, right? So we have like m times n in total, m times n in total, the numbers, and then we append them to here, right? And then we do a sort. So the worst case scenario, we're gonna be a m times n log mn. That's basically time complexity. So yeah, because for the union find the we are after the path compression, we are assuming it's like it's close to O1. You know, that's why even though we have a for loop here, but that's only for the numbers, only for the same numbers. Okay, so it's not looping through everything. That's only to loop to make sure the same numbers on the same column, row and column, are in the same group. And space complexity is is m times n, right? So it's obvious that's in total we have this many numbers. Okay. All right. So just to recap this problem real quick, right? So first thing first. So you need to know to be in order to solve this kind of a rank transform from either a array, which is that's an easy problem, or a matrix. The basic idea is to sort these numbers first, and then we process those numbers from the smallest to the biggest. And another thing is that since this problem is 2D array here, so which means that not only we need to not only we need to satisfy the conditions on the row, but we also need to satisfy on the column. That's why we need to maintain like this row max rank and the column max rank, so that later on one location we can use the previously calculated results to get the maximum, and then we do here we do a plus one. Okay, so that's the second, and the third is the most tricky one. How about the same value? How about what if we have the some numbers on the same row and column, right? And we cannot only using this row and column for both of the numbers, because later on when we calculate this one, if we use that one, I mean this rank could be different, and then we also need to update these numbers. That's why we're using like a greedy approach. So at the beginning, when we are calculating the the ranks for the same numbers that's sharing the same row and columns, we'll be we'll be collecting their the row and the max values all together, and then we'll get the maximum out of all of them to use as the new rank for all those the numbers. And in order to do that, we have to somehow group those numbers with the same row and column. And we could use DFS or BFS to explore them, or we could have used the union find. That's why after creating this like value to pass dictionary here, for each of the values here, I'm creating a union find array. So the reason I'm creating the union find here is because, like I said, it's the union find for each of the value. It's not for the whole array here, for not the for the whole matrix. So it doesn't. I mean, we could have like a union. We could have put this parent on on the top, but in that case, we have to introduce like a new value, like a key for each of the value, which it's overkill. So instead, we could have just defined like a parents for each of the values inside the for loop here. And then the next is we just group those union together with those co coordinates together, and then we are basically calculating the rank for each of the root, and then we update by following this. It's like a greedy approach, right? Cool, guys. I think that's it for this problem. Yeah, thank you so much for watching this video, guys. Stay tuned. I'll be seeing you guys soon. Bye bye.